I would never eyeball that in a million years. That's a weird fraction. So it's good that we have a way to solve for it exactly so that we don't have to guess, because I don't think anyone would have guessed 2/7. If you would have, I don't know what to say, but it seems unlikely to me. So 2/7 is our x coordinate, and now we can plug in x equals 2/7 and solve for y. So maybe y is equal to 3 times 2/7 plus 1. So that's 6/7 plus 1. So y is equal to, that should be 13/7. So that's another really weird fraction that I don't know who would have ever guessed. But there we go. The coordinates of this corner point are 2/7, comma 13/7. We found those coordinates exactly just by solving the system of equations for these two lines that intersect there. Okay. So I can pause here for questions. Okay. And so if there are no more questions, then let me just say one more thing, probably. So this is finding corner points. This was finding corner points. Again, so just to summarize, to find a corner point, we just solve the system of equations, system of two equations for the lines that intersect there. Okay, so the two lines that intersect at that corner point, we put them into a system of two equations, and then we solve that system, and that gives me the corner point. I'd like to point out a certain situation that a lot of students have been confused about before. Let's say my feasible set looked like this. You know, I graph my lines, and I get something like this. This is good. This is okay. This is like an example I would like. Let's say my feasible set is right here. Right, so I graph all my lines for my inequality, and it turns out that my shaded feasible set is right here in this little, how many sides is that? Is that 6? No, it's 5. Okay, so this little pentagon here. So this is my feasibility set. I would just like to point out that the only points here that are corner points are the things that touch the shaded region, right? So only the corners that are touching the shaded region are corner points. I've had students in the past be tempted to talk about these other intersection points, like down here, for example. They maybe want to try and think of this as a corner point, but we don't have to worry about where lines are intersecting away from the shaded region. I only care about corner points that are touching my feasibility set. Anywhere else, we're going to end up ignoring those, so you don't have to find them. So if you end up graphing a system of inequalities and it looks something like this, where not only do you have these intersections along the feasibility set, but you have other weird ones away from it, you can ignore those ones because we only care about corner points touching the feasibility set. So I just want to make that abundantly clear. Save yourself some trouble, just in case. Okay. So maybe the last thing is the following. Just looking ahead, why are we doing all this? So just looking ahead, just to give some motivation as to why we're doing this. And of course, we'll go into detail about this next week. It turns out that there is a fact that's going to be very helpful for us, which is that if P is a function, then if I give you a system of inequalities, so I'll just write it this way. So if I had some system of inequalities and I graph their feasibility set, and I give you some function like I will in the linear programming world, you'll be given a function that we want to maximize or minimize. It turns out that the maximum and minimum of P are at a corner point. And I'm going to put this little caveat that says if they exist. So the point, the upshot of this, I suppose, is that when it comes to the linear programming problems where we need to find the maximum or minimum, given your constraints, it turns out that we're only going to have to check our function at corner points in most cases. I wrote if they exist. So remember yesterday I talked about, we had some feasibility sets, like something that looks like this maybe, or this goes off forever, that were unbounded. There will be an issue where if I have an unbounded feasibility set, then there might not be a maximum or minimum because the function might just get bigger and bigger as it goes off forever, or smaller and smaller as it goes off forever in one direction. And so in this case, there might not even be a maximum or minimum, and so this point is kind of moot. But if it's bounded, then I just have to check at the corner points and I'm good. So next week we'll talk about that in detail, and we'll also talk about how to deal with this unbounded case, because there is still a way to work with it, but we just have to be a little more careful. There's some extra steps involved. But that is where we're going next week with all this stuff, and this is why we care about corner points, because it gives us hope for finding the maximum or minimum of a function. Thus, we'll be able to solve the linear programming problems that you guys set up in 7.1. Okay. Let me think. I think that's all that I really want to say about this section. So does anyone have any questions?
Would you care to do one more example of finding the corner points?
Yeah, I don't mind. I can do that. You want me to just kind of, so my question is, do you have one in mind, or do you want me to just do one?
Just any, really,
Sure.
Just another example.
Yeah. Give me 1 second then, and I'll pull one up here. I can try to make one up, but I don't want it to end up being too complicated, so I might just steal one out of the book or something. Okay, I think maybe I like this one out of the book. It doesn't look like it'll be too painful for us to do. So let's do another example. Okay, so here's our system. It'll have 3 inequalities. Actually, I can mention another fact to you. This is actually good, so I'm glad you asked. X minus y greater than or equal to -4. X minus 2y less than or equal to -2. And 5x plus 2y is less than or equal to 10. So we'll take this system of 3 inequalities, and we'll go ahead and graph it, and then we'll look for the corner points. So maybe I'll do my graph. Well, let me do this first. Let's write down the equations that we're going to have to graph the inequalities. We'll need them later also. So turn this into an equation. I get x minus y equals -4. X minus 2y equals -2. 5x plus 2y equals 10. So I'll just convert those. And for my own sake, and just because it simplifies things a lot, I'm going to solve all of these into slope-intercept form. You technically don't have to do this part, but I'm going to do it. I've been doing it. I'm going to keep doing it. I'm going to solve all these into slope-intercept form. It just makes our lives a little easier. So like, I could add y to both sides and add 4 to both sides. So I think I get x plus 4 equals y. Would be the same for this guy. X plus 4 equals y. Here, if I were to subtract x from both sides and then divide by -2 on both sides, it looks to me like I should get y equals 1/2 x plus 1. I think I did that right. Yes. And then if I do this guy here, I'll subtract 5x from both sides, and then I'll divide both sides by +2. So I think there I'll get -5/2 x plus 5. Maybe rewrite it to the left a little so we have more room. Rewrite this guy too. Kind of sloppy. That was 1/2 x plus 1. this was 5 halves, negative 5 halves x plus 5. So that's just converting these into equations and then solving them for y so that they're in slope-intercept form. Because it just makes computations and graphing easier for us. Okay, so I think I can hopefully get away with drawing my coordinate axes like this. So we're going to graph it so we can get an idea of where our corner points are, and then we're going to find the corner points. So, okay, let's go ahead and do this. Let's do our first guy. So I'll do them in colors again. So let's do this first one in red. Y equals x plus 4. That's a slope-intercept of 4, and a y-intercept of 4, and a slope of positive 1. So it looks like when I go to the right by 1, I'm going up by 1. So something like that. For the next one, got y equals 1/2 x plus 1. So y-intercept of 1, a slope of 1/2. When I go to the right by 2, I go up by 1. Oh, maybe I should have drawn them the other way. We'll see how this is going to go. And then finally, I have, maybe in blue, we'll draw this guy. Yeah, I think I might have to redraw this one annoyingly, but that's okay. It'll give me an idea of the shape. That's one problem of doing this. This is a problem I didn't prepare, but I guess I did it on the one I prepared for also. So I don't know what my excuse is. So we take a y-intercept of 5, and we take a slope of negative 5 over 2. So when I go to the right by 2, I go down by 5. So that gets me all the way down here. Okay. So I think what's going to happen, when I check where the shading is, again, we should test points for each of these to find out where the shadings are. But I think what's going to happen is we're going to be in this slice down here. Down here. And so if I had drawn this correctly, and I'll sort of redo it over here. It looks like this should happen. It looks like this should happen, and I should get this like long skinny triangle that intersects over there off to the left, which wasn't in my picture here. So it should look something like this. And so I should have 3 corner points again. I have this big long triangle. All right, and since I told you guys not to eyeball the coordinates anyway, let's ignore the fact that I kind of sloppily drew this over here as a sketch. But that's okay. It gives us sort of a guide just to see where the lines should be and where, or how we're going to find our corner points. So, okay, I'm going to erase the bad drawing. So now that we know what this kind of looks like, let's find the corner points. And I might mention a certain, well, I'll do that at the end, actually. Let's find these corner points first, and then I'll mention a fact to you. Let's find the corner points. So I don't know, let's find this one first. We'll find this one first. So we just ask which 2 lines intersect there. In this case, it's the purple line and the red line. So that's these 2 lines. So I'm going to take these 2 equations and put them in a system. So that's y equals x plus 4, and y equals 1/2 x plus 1. So I just took those 2 equations because those 2 lines intersect at that point. And so now I'm going to solve this system. And because I wrote these in slope-intercept form, they're solved for y already. So this is basically